The key elements of the titration curve is one titrant and one analyte. Titrant is the species that have a known concentration, and then you add it into a flask. Inside that flask, you have a solution. That solution has a name called the analyte. So most of the time, you don't know the concentration of your analyte, but you do know the volume of the analyte. For the titrant, it's actually the opposite. You know the concentration of your titrant, but you don't know how much of titrant you add to your analyte, so that the concentration of your titrant and analyte are actually equal to each other. For the titrant, we only use strong acid or strong base. But for your analyte, it can be strong acid, strong base, weak acid, weak base, or buffer. When we do all these titration things, we actually want to know how the pH of your analyte changes. Eventually, what you're going to do is want to make a plot. On the y-axis, it will be the pH of your analyte. On the x-axis will be volume of your titrant. Okay, so let's do a quick thought experiment. Your titrant, let's say, is a strong base, for example, sodium hydroxide. And your analyte is your HCOOH, a weak acid. Okay, if I want to actually plot out this titration curve, this is pH 7. Before I add in any titrant, what kind of solution do I have? Acidic solution, right? Therefore, the pH should lower than 7, right? So you know the curve will stop somewhere below 7. And then you're going to add in your base. So once you add in base, what happens? The pH is going to increase slowly. At a certain point, when you do your Jenkins experiment, at a certain point, you'll see a quickly pH jump. When you see that happens, you're going to reach a point that's called the equivalence point, where this point means actually you have the same amount of titrant and analyte. Okay, so number of mole of titrant is going to equal number of mole of analyte. And then it's going to reach another plateau. Okay, so this will be actually a typical titration curve you should expect if you have a titrant as a strong base, you analyze acid. Here, we are going to pay attention to 4 different zones. Zone number 1 is before you add in any titrant. So zone number 1 is no titrant condition. Zone number 2 is before your equivalence point. Okay, so I will call the equivalence point just EP. Zone 3 will be at equivalence point. And then zone 4 will be after equivalence point. So what we are going to do today is actually, if I give you a system, a titration system, can you calculate the pH at these 4 different zones? The general approach is solve a question like this. Follow 4 steps. Step number 1, you want to know what is your titrant, what is your analyte. Okay, so that you will know what solution you have in the very beginning. Step number 2, you want to write out the ionic equation. Here we're going to write out 2 different ionic equations. One is so-called the complete, and then the other one is called the net ionic equation. The third step is actually you want to calculate your VEP. You want to know after a certain amount of titrant, you will actually reach the equivalence point. And the equation you're going to use is number of mole of your titrant is going to equal to the number of mole of your analyte. So that you can actually figure out what is the volume you will need to reach your VEP. And the very last one is calculate the pH at 4 zones. So there will be actually the 4 steps we are going to use for all the questions in this chapter. Okay, so this is actually the first questions that we are going to do. We want to talk about the strong acid, strong base situation. In this example, you have 0.1 N sodium hydroxide solution, and then you have 0.1 N HCl solution with a volume of 100 ml. Step number 1, list out our titrant and analyte, right? So what is your titrant? NaOH, right? And its concentration is 0.1 M. Who is actually your analyte? HCl. Concentration 0.1 M. Volume 100 ml. Second step, write out the ionic equations. When you have a solution contains sodium hydroxide, it's strong base, so it dissociates 100%. Therefore, you know inside your solution, for your titrant, you're going to have sodium plus and OH minus. Then for your analyte, you have HCl, right? HCl is a strong acid. Then you're going to have H plus and the Cl minus. So the acid is going to interact with your base. Therefore, you know this guy, they are going to interact with each other, going to give you just H2O. And then you still have sodium plus and the Cl minus inside your solution. The things we just finished is so-called the complete ionic equation. But if you look at this equation, sodium appears on both sides, so you can ignore it. Chloride is the same. So the things that actually matters and contribute your OH, it will be OH minus plus H plus. That give you H2O. That is so-called the net ionic equation. The third step is to calculate the equivalence point, the VEP. Number of mole of titrant is going to equal the number of mole of your analyte. Our titrant is sodium hydroxide. We don't know the volume, how much of sodium hydroxide I should add into my analyte so that it will reach the equivalence point. But for your number of mole of analyte is actually well known, right? Because you know it's 0.1 N, 100 mil. So you can actually calculate the number of mole of your analyte is just equals to the concentration of your analyte times the volume of your analyte, right? Number of mole titrant, you want to use the titrant concentration times certain volume, then to add in, so that the number of mole of titrant is going to equals to the number of mole of analyte. Therefore, you know your VEP is going to equals to concentration of your analyte times the volume of your analyte divided by the concentration of your titrant. In the first part, we actually know that is the concentration of your titrant. That is the concentration of your analyte. That is actually the volume of your analyte. Therefore, we can actually calculate the VEP very easily. So that's 0.1 times 100 mil over 0.1. So this will give you just 100 mil. What this means is that after you add in 100 mil of your titrant, then your system is going to reach equivalence point. If today I say, okay, I only add in 50 mil of titrant, the solution you're going to have will actually fall within zone number 2, right? So if I say I add in 110 mil of my titrant, then you know you are actually at zone number 4. So knowing your VEP is very important because it's going to tell you which zones you are. So then we want to do step number 4, right? I want to calculate pH at different zones. Calculate the pH before you add in any titrant. So apparently this is actually zone number 1. Now you need to ask yourself, what solution do I have? Before you add in any titrant, that means actually the solution you have is just pure analyte, right? And then you know your analyte is HCl solution, right? And the concentration is 0.1 N. So what solution do you have? Strong acid, right? So you know the proton concentration would simply equals to your acid concentration. That's going to give you 0.1, right? So pH is negative log of your proton concentration, going to equal to negative log of 0.1. That gives you a value of 1. How about the second one? Okay, if you add in 30 ml of NaOH, titrant is 30 ml. And then you know your VEP is equals to 100 mil, right? So by comparing these two, you will know you're actually in the zone 2 because the amount you add in is less than the amount you should have for the equivalence point. Therefore, you know you're actually at zone 2. When you are at zone 2, what do you have inside your solution? To understand this, it's better to actually write out your net ionic equation. OH minus plus H plus, that give you H2O, right? So in the beginning, you know you have 0.1 N, 100 mil of acid from your analyte. And then right now you add in 30 mil of your base, concentration is also 0.1. Once you do this, you know acid bases, they are going to always interact with each other, right? So this one apparently is a limiting reagent. So this one will be consumed fully. You're going to consume all of your base and produce that many water. And then once you reach your equilibrium, all the base are gone because they are consumed by the acid. So in the end, you have, this will be 0.1 times 70, right? And then this just 30 times 0.1. So you have less many more of acid still existing inside your solution. Okay, number of mole of your proton is that much, right? But the things that you really need is actually the concentration to calculate your pH. So right now you know number of mole is 7, right? What is the volume now? Originally in your analyte you have 100 ml, right? Right now you add in 30 ml of your titrant. Therefore, the total volume of your solution will be 130 ml, right? So that is actually how you calculate the concentration of your solution at zone 2. The things that is really different is the total volume of your analyte changes, okay, when you add in different amount of titrant. Okay, and that will actually affect the concentration of the proton. So this is actually the part that you want to actually recalculate the concentration. In the ice table, we always do the mole here. So we did not actually change the concentration. Okay, we actually change into the concentration later. So once we have this, then the pH will simply equal to negative log of this value. Yes, that is actually from 100 ml of your analyte plus 30 ml of your titrant, because on the top of the question you add in 30 ml of NaOH. Okay. Yes. 1.27 for the pH. So you can see if you add in some of the base into that, okay, the pH go from 1 to 1.2. So here is actually relatively simple because you know you still have your analyte outweighted than your titrant. So in the strong acid-base condition, in this case, all you have is a strong acid remaining inside your container. Therefore, the solution you have is still strong acid. The only thing you need to do is recalculate the proton concentration due to the change of the total volume. Let's look at the part C. You add in 100 ml of sodium hydroxide. Now your V titrant is 100 ml. And you also know your VEP is 100 ml, right? So you know you're actually at zone 3. At zone 3, that means you have the same amount of acid, the same amount of base. You have the same amount of OH minus, right? The same amount of H plus. They are going to interact and consume each other because they are actually the same amount. So all of them will be consumed. All you have is what? Water. So what is the pH of water? 7, right? The very last one is if today I add in 100.5 ml of sodium hydroxide. So right now you know your V titrant is 100.05, which is actually larger than your VEP, right? Therefore, you know right now you have a solution that have already passed your equivalence point, right? So we know you are at zone 4. Okay, so in the beginning we know in our analyte, we have 0.1 m HCl, right? We have 100 ml. We have that many moles of H plus. Right now, you add in 100.05, right? Concentration of OH minus actually 0.1. You have 100.05. Apparently, we have more base than the acid. This becomes the limiting reagent, right? And that guy will be consumed completely. When you reach equilibrium, this will be 0 for your H plus. For your OH minus, you have 0.1 times 0.5, right? Therefore, you know the number of mole of your OH minus is simply equals to 0.1 times 0.05. But the things we care is actually the OH minus concentration, right? So you want to actually calculate your OH minus concentration, which can be obtained from the number of mole of OH minus divided by your V total. Okay, so your V total will be the volume of your analyte plus the volume of your titrant. Number of mole of your OH minus is actually 0.1 times 0.05. Volume of your analyte is 100, right? Volume of your titrant, 100.05, right? So you can actually calculate your OH concentration. Then you can calculate your POH. It's going to equal to negative log of your OH minus concentration. So that's 4.6. then what is your pH? It's going to be equal to 14 minus 4.6, right? It's 9.4. I want to actually get back to this value again, okay? So you know, before you add in any titrant, you have a pH of 1, right? Okay, add in 30 ml, like go from 1 to 1.2. So you can see the increase is not a lot. But once you add into 100, pH jump to 7. It actually goes up like this. It goes slowly in the beginning, but when you're close to your equivalence point, you're going to see a huge jump in your pH. And then after that, you just add in 0.05 mil more. So you go from 7 to 9.4. So you can see the pH is going to change like crazy around your equivalence point. If you actually redo these experiments, if you plot your pH and then x-axis is the volume of your titrant, then you should expect to see increase slowly and then shoots up quickly and then going to be like this. Okay, so once you actually map out this curve, you can actually know where is actually your VEP, right? So let's actually, you have this curve, you can find out the kind of center point. There will be actually your VEP. Based on our current situations, I also want to emphasize, at your zone 1, all you have is just a strong acid solution. How about your zone 2? You still have strong acid solution, right? Because all the base you add in was consumed. You just have less concentrated strong acid inside. Zone 2 is still a strong acid solution. How about your zone 3? You have the same amount of acid base and they are going to consume with each other. Suddenly, all you have is just water. Therefore, your pH is actually 7. How about zone 4? At zone 4, you have strong base goes into water, right? Then you have a diluted strong base solution. So in this case, the calculation of your pH or pOH is very simple, right? Because all you need to do is actually calculate the amount of base divided by the final volume of your solution. Then you can get your proton concentration or base concentration. Therefore, you will know the pH of your solution. So this is actually the simplest case that you're going to have. And then here, in this case, our titrant is a strong base. Our analyte is a strong acid. Now I want to ask you, if I flip these things around, if my analyte is a strong base, if my titrant is a strong acid, how this curve will change? In the beginning, in your zone 1, all you have is actually a strong base solution, right? Therefore, you should expect your pH is going to be larger than 7, right? Because you have strong base. So pH is actually going to be close to 14. And then when you add in acid, you can see the pH is going to decrease gradually. Nearby the equivalence point, you're going to see a sudden jump of your pH. And then after the equivalence point, you're going to have a strong acid solution. Therefore, the pH is going to keep decreasing and reach a very small value. To translate the things we just said on the plot, you should expect something like this. So this will be actually your titrant is strong acid, your analyte is strong base. You really need to know your system because once you know your system, you can actually predict how it should look like already. When you plot these things out, it's very easy for you to identify, okay, where you are. Then you know what solution you have. Therefore, you know what equation to use.